Well, good afternoon, everyone, and welcome to the latest installment of Chafee's Brown Bag series of math and science. And today we're going to get mathematical. The title of my talk is Creating Good Equations for the Classroom. More specifically, rational equations, logarithmic, and square root equations. Well, we're math teachers, or at least some of us are, so we don't just solve equations, we have to create them. And the equations we create have to be solvable by the students. Now, I'm going to be focusing on quadratic equations, an equation having the form ax squared plus bx plus c equals 0, where a, b, and c are numbers, and x is the variable you have to solve for. This equation is not necessarily easy to solve, and if the students haven't yet been taught the quadratic formula, or if they don't know about complex numbers, it may actually be impossible for them to solve this. So as a teacher, I have to choose A, B, and C wisely so that my students will not be overwhelmed with an unsolvable equation. Now, if the equation can be solved by factoring, in other words, if I can take this trinomial on the left side and if I can factor it into something times something, then in fact these solutions will be rational numbers, such as -2 or a fraction. That would be if the equation can be solved by factoring. Well, what if it can't be solved by factoring? Well, actually every quadratic equation can be factored depending on the numbers you're allowed to use, but in the typical undergraduate math classroom, you're only allowed to use whole numbers factor. And if it's not factorable in that sense, then you're going to need to use the quadratic formula, and the solutions will be rational numbers. They'll have the form whole number plus or minus an unsimplifiable square root divided by something, or they may contain the mysterious I, the square root of -1, which we want to stay away from right now. So we want the solutions to be rational numbers. Or at least, if we want rational solutions, we can't choose those parameters A, B, and C randomly. We have to choose them wisely. Now, for some of the purposes here, I need to point out that it's easy to create a quadratic equation with rational solutions. That's not a problem. The difficulty is if you want to create a rational equation, one with x in the denominator, or a square root equation where you have the square root of x, or a logarithmic equation where you have the log of an expression containing x. But if you want to just create a quadratic equation with the rational solutions, it's easy. Just start with two rational numbers that you want to be the solution. Call them R1 and R2. And pick another rational number A, which could be 1. And then just multiply this expression, A times x minus R1 times x minus R2. And if the result of multiplying, if we call it this expression here, then the solutions of the equation, that expression equals 0, are the R1 and R2 which you selected. So that's easy. But what if you have to create a rational or square root or logarithmic equation? Well, I've done some Googling and I haven't found any papers or sites which give methods for systematically creating equations like those, which are guaranteed to have rational solutions. So I've discovered several such methods, and in this talk I'm going to show as many of them as I can fit into the available time. Now, so I'm going to start with the rational equations with fractions where x is in the denominator. And my researches began when I had to write a test question of the following type, taken from our intermediate algebra textbook. And in general, it's like this. Worker number 1 can complete a job in T hours when he works alone. Worker number 2, working alone, can complete the same job in T minus A hours. He's more efficient. Now, the reason I say minus A, rather than giving a number, is the challenge for me is to find a value of A, which will make the equation solvable by the students. Well, the problem continues. Also, it takes B hours to complete the same job when they work together. So in that situation, how long does it take worker number 1 to finish the job if he works alone? So again, my problem is find values of a and b, which will make this problem solvable by the students if they don't have a calculator with them. Well, what you do is you look at the rate of work. Work rate is defined to be amount of work done divided by the number of hours that it takes. So the rate for worker 1 is 1 job divided by t hours. That's how long it takes him. Here's the rate for worker 2, 1 job divided by t minus a hours. And when they work together, this is their net rate, 1 job divided by b hours. And the equation comes from the fact that when you add the rates, the individual rates of the two workers added together have to equal the net rate. It produces this equation. 1 over t plus 1 over t minus a equals 1 over b. The variable is in the denominator. I have to choose a and b so that this equation is solvable by the students. Well, what we do is we find the least common denominator, which is b times t minus a. And we multiply each side by the LCD, and after a few steps we have this, and that's a quadratic equation because a plus 2b is a number and so are ab. Well, we can call that the reduced equation because that's what you get when you clear fractions from both sides of the equation. Well, we can apply the quadratic formula to this equation here to get the answer. Now that's not cheating because I'm allowed to use the quadratic formula even if they're not. I would need to know under what conditions do I get a rational solution. Well, here's the solution here, and notice it's got a square root in it. So if I'm not careful with a and b, the solution is going to be something with a square root. I don't want that. Now, so how do we get this done? Well, in this paper we assume that all equation parameters are rational numbers. So a and b are rational numbers. How can we make the square root of a squared plus 4b to be a rational number? Well, to do that, the a squared plus 4b has to be a square, so that when you take the square root, you get a whole number. So this expression needs to be a square like 4 or 25, or even 49 over 121. The square root of this guy would be a rational number. Okay, let's see. So notice this. A squared plus 4b squared, that's a squared plus the quantity 2b squared. We need a squared plus 2b squared to equal a square. I wonder, under what conditions is a number squared plus another number squared equal to a square? Well, I'm not using PowerPoint here, so the answer is right there. Kind of spoils the suspense. Well, if they're part of a Pythagorean triple, like 3, 4, 5 or 5, 12, 13, the sides of a right triangle. Okay, so if a and 2b equal 3 and 4 or 5 and 12, then this word problem will have rational solutions. So hey, let's try it. Let's try 5 and 12. So if a is 5 and 2b is 12, meaning b is 6, then this equation becomes that equation. If you clear the fractions, you do indeed get an equation which factors. So either t minus 15 equals 0 or t minus 2 equals 0. The solutions are 2 and 15. They're rational numbers. We've succeeded. Okay. Just want to point out, if t equals 2, then worker number 2's time would be t minus 5, which would be 2 minus 5. Well, that's not valid. He can't do it in a negative number of hours, no matter how efficient it is, so there's only one valid solution. But we've achieved our general goal. We have rational solutions. Well, I just want to point out that a and b don't have to be whole numbers. If I take this equation here, and I divide each side by 25, now I have 5 squared over 25 plus 12 squared over 25 equals 13 squared over 25. In other words, plus or minus 1. It could be plus or minus 1 squared. Now, for Pythagorean triples, we reject negative numbers, but hey, in an equation, they can be negative. Why not? Plus or minus 12 squared would be the square of a rational number, so we could make a and 2b equal to these values. And if I do, I have this equation here, and the solutions are, they're rational numbers. Now, one thing you could do if you're a little skeptical about this, you could say, well, hey, what if I change that 6 to a 7? You know, you could say, well, maybe they're always rational. He's just pulling the wool over our eyes. Well, no. If you put a 7 in there, you will find that the answers are not rational numbers. So yeah, you do have to pick the values wisely. Okay, so actually for the type of equation I'm talking about here, there we go. For this type of equation, we can give necessary and sufficient conditions for the solutions of the equation to be rational numbers. Now, I haven't found necessary and sufficient conditions for any others, but since I did find it for these guys, I just thought I'd show off a little bit. So let's talk about in general. Well, let's start with the classic definition of a Pythagorean triple. Any triple of positive integers x, y, z for which the first component squared plus the second squared equals the third squared. But for us, hey, they don't have to be positive integers. They can be rational numbers. They could be fractions. They could be negative. So why don't we define a generalized Pythagorean triple? Any triple of non-zero numbers alpha, beta, gamma. Maybe I should have said alpha, beta, never mind, delta. Never mind. Alpha, beta, gamma, such that alpha squared plus beta squared equals gamma squared. We could call that a generalized Pythagorean triple. And then we could say a standard Pythagorean triple is what they are if they're positive integers. Well, so what we need to talk about here is Pythagorean pairs. Would be just the first two components of a Pythagorean triple. And so then alpha and beta would be a Pythagorean pair if and only if alpha squared plus beta squared equals the square of a rational number. Well, it turns out, I omit the proof, it turns out that two numbers form a Pythagorean pair if and only if you start with the first two components of a normal Pythagorean triple and then multiply any non-zero rational number times plus or minus x or plus or minus y. So those will give you a Pythagorean triple as I've defined it. And then with that definition, we have this theorem. This equation has rational solutions for t if and only if a, 2b form a Pythagorean pair. So the theoretical problem of finding a and b to make the solutions rational, it's been completely solved. Also, I want to point out that it's not in this paper, but needing to have a Pythagorean pair is not actually very restrictive. Actually, I can pick any number to be a, and then there are an infinite number of choices for b that make the solutions rational. So I've got plenty of problems to give my students. I can keep teaching forever and never run out of them. All right. Now, but I mentioned there's two basic approaches to creating these equations. I showed you the theoretical approach. There's also an empirical method. And when I discovered this method, I just did, if only I'd thought of that before. Because it's so easy. But let's remember that this is the equation. We want to pick a and b to form rational solutions. Hey, let's just pick any value of a, like 7. Okay, if a is 7, there's your equation. And suppose we would like the solution to be t equals 9 hours. Well, that means the equation is true when I plug in a 9 there and there. Okay, so that means this equation is true. Well, that's really easy to solve for b. In fact, the solution has to be a rational number. And if you have a TI-89, like I do, it's had a lot of use because it's very useful. There's the solution. And that's a rational number. So here's the equation. It's guaranteed to have rational solutions, and according to my trusty TI-89, there are the solutions. So it's even easier to create rational solutions than I first thought. Well, I thought I'd take some time to just a little while to define, give a name to what we're trying to do here. So this equation is really a family of equations depending on two parameters, a and b. And we're trying to find values of a and b that will make the solutions rational. So why don't we define a rationalizer of solutions to be a pair of values for a and b that will make the solutions rational. And so what we're doing is we're trying to rationalize a equation family. We're trying to rationalize the equation. All right. Well, but I want to show you some more theoretical methods for working on equations like these. So here's another method. Now there's another word problem on the same page of our textbook as that first word problem without all the details that leads to this equation, 1 over x equals 1 over x plus a plus 1 over b. It's a lot like the previous problem, except now the two x terms are not on the same side of the equation. If you multiply by the LCD, there is your quadratic equation. If you apply the quadratic formula, those would be the two solutions. So for rational solutions, we want to make this square root equal to a rational number. Well, we could use the method of Pythagorean pairs. We need a squared plus 4ab to be equal to one number squared plus another number squared. You could do it like that. Define a to be plus or minus alpha. Define this expression to be plus or minus beta. It works. But let me show you another method. Another method. I call this the method of equal discriminants. So in this method, you just start with any old quadratic equation where you know the solutions. So I just say 2x plus 3 times x minus 5 equals 0. So either 2x plus 3 would have to equal 0, or x minus 5 would have to equal 0. I know those are the solutions. And I can use this quadratic equation to create an equation, a rational equation of the form I showed you, which does have rational solutions. Well, remember the definition of the discriminant of a quadratic equation. If this is your equation, now I'm switching to lowercase just because that's more customary. The discriminant of the equation is defined to be b squared minus 4 times a times c. So the discriminant of the equation above would be 169, which is a square. And also remember the theorem which says this equation has rational solutions if and only if d equals the square of a rational number. And indeed, the discriminant is 13 squared. All right, we're going to use that to get rational solutions for this equation. Well, let's see. So previously I cleared fractions on this, got a quadratic equation for this, and that was the discriminant of that quadratic equation. So I could call this the discriminant of that rational equation, which I define here, the discriminant of a rational equation. But let me show you how it's done here. So in fact, we can create an equation having that form whose reduced equation has the same discriminant, therefore its solutions are rational. Well, what I do is I say, hey, I'm going to make the discriminant of this guy, and I'm going to express it, the discriminant, in that form. Now this equals 169, but I need it in this form. I'm going to set this discriminant equal to the discriminant of my rational equation. So now if a squared equals 49, and 4ab equals 4 times 30, I'm going to have rational solutions of my rational equation. You know, it just, by the name, it sounds like a rational equation should have rational solutions, but no, it just doesn't work that way. We have to work for them. Okay, so if a squared is 49, a is plus or minus 7. And a times b has to be 30, so b would be 30 divided by plus or minus 7. Gives you two ways to do it. So here's one where a is 7 and b is positive 30 over 7, so there's 1 over b. This equation does turn out to have solutions 3 and negative 10. Now remember that we started with an equation having these solutions. The rational equation doesn't have the same solutions as the one we started with, but in fact, if you multiply these guys times negative 2, we do get those solutions there. And the equation, the quadratic equation we started with, does have a leading coefficient of 2. Yes, it had a coefficient of 2. So there is a connection there. So yeah, that's the method of equal discriminants. And just here's a summary of it. So create your own solvable quadratic equation, x plus b equals plus c equals 0. And then set his discriminant equal to the discriminant of that equation, and you will have rational solutions. The details are in my paper there. But I wanted to point out one specific result of this. If you give me two rational numbers, I can give you an equation of that form which has your rational numbers as solutions. That's the equation. So you can not only guarantee rational solutions, you can know ahead of time what they are. Very useful. All right. Well, I want to show you some other kinds of equations. Moving away from word problems, well, sometimes the math teacher would like to give his students an equation of this form. Notice the two denominators on the left are x plus a and x plus b, and there they are on the right side. What that means is the lowest common denominator for all three fractions would be x plus a times x plus b. I'd like to be able to pick the coefficients of this guy so that the solutions will be rational numbers. And I gave an example here, and I didn't pick them correctly, and what do you know? The solutions are imaginary, so I cannot give them to my Math 410 students. So how can you pick the parameters? Well, the simplest way to do that is to use the method I call substitution of parameters. We've got the parameters a, b, c, d, e, f, g, and h. Assign arbitrary rational values to all but one of them. And so the student won't have a difficult factorization. Make your unspecified parameter one of the numerator values. So here's an example. I arbitrarily chose values of the other parameters. I just want to know, well, what's h going to have to be to make a solution they can handle? Well, for example, if you want one solution to be x equals 5, then this equation must be true when you plug in 5 for x. You get this equation here, which simplifies to that one. Again, if you have a TI-89 or wolframalpha.com or Mathematica, it's easy to solve this. Actually, it's probably not that hard to solve it if you just use a pencil. There's the answer. So this equation is guaranteed to have rational solutions, and it turns out the solutions are 8 and 5. It worked. Yeah, that generally the method of substitution is the easiest way to do it. You plug in values for all but one value, and for the type of equations I'm studying here, you're going to get a rational solution, so it'll work. Okay. I also want to point out we can also specify both solutions. So in that case, choose all but two of the parameters. So here I'm not specifying f or h. I'm going to specify them by specifying two solutions. If 5 is a solution, then we have this equation here. And if -3 is also going to be a solution, we have this here. So that results in a system of two equations with two unknowns. And again, with technology, it's relatively easy to solve. And it's a linear system. I don't want to find that f is the square root of 5. That's no good. I need the solutions to be rational numbers. Well, they are because they're in the numerator. And it turns out the solution to this system is f equals 23, h equals -44. Now, before I give the students this equation, I want to vet it. I want to make sure that when I multiply by the LCD, I don't get really big numbers, making it hard to factor. But I think this one works out fine. Yeah. Now, one thing that the math instructor has to deal with also is extraneous solutions. For certain classes of equation, if you do all your calculations right, you can still wind up with the wrong answer. So for certain classes of equation, including these guys, where x is in the denominator, you have to check your answers by substituting them into the original equation to make sure that your answer does not make a denominator 0. So the teacher has to also give his students problems with extraneous solutions. So how can we guarantee an extraneous solution? That's a little harder, but here's one way to do it. So here's our equation of this form. And notice that one of the denominators is x plus a. If you get x equals -a as a solution, that's extraneous because when x is -a, the denominator here would be 0. Well, -a will be an extraneous solution of this equation if and only if h equals this expression here. So you pick a, b, c, d, g, and a, and h is determined by this one. That will give you one extraneous solution and one non-extraneous solution. And I mean, here's a quick example of that. I start out with these values. I just need to find h. That's the only unspecified parameter. So here a is -2. And so h would be this expression here. Calculate it out. The answer is it's 14. Gives you this equation. Looks innocuous enough. Here's the equation when you clear fractions and factor it. One of the solutions is x equals 2. But wait. It's extraneous. You got to throw it out. So we didn't get 2 because we goofed. We got 2 because this is one of those sneaky equations that sometimes throws a curveball at you. Just to give you an idea of what sort of things you can discover about these equations, here's another result for the same form of equation I'm talking about. If c plus e equals 0, if this coefficient of x plus that coefficient of x is 0, then when you clear fractions, you get a linear equation, not quadratic, and there's guaranteed to be one rational solution. So if you just need a quick example, it's really easy. You know, you can be sort of you can do a mathematical magic show. Write a very complicated looking equation and say, I'm sensing that if I make this one -2 and that one 2, there will be one solution. I know. Now, if c plus e is not 0, well, we need to find 8 parameters. Well, if you choose all the parameters except h and plug in h equals this value here, where I can be any rational number, you're going to get rational solutions. Now, I think this one you could set up software to generate these equations algorithmically. I think that could be an important issue for creators of mathematical educational software. You want to be able to algorithmically create equations that will not be too difficult for the solution. Of course, maybe the writers of these programs have discovered these facts already and they're keeping them hush-hush. I don't know. I just haven't been able to find it Googling. Well, now I'm making it public, so I hope they don't get mad at me for spilling the beans. Okay. Now that result that I showed you is a little bit inelegant. It turns out that we can get a little bit of a more elegant result in this way. So again, here is our equation. And again, we're going to specify all the parameters. We're going to choose all the parameters except h arbitrarily. Just pick any values you want. If h is af plus bd, a times f plus b times d, a little bit like a determinant, then you have rational solutions, namely 0 and this value here. So this is another way you can pretty quickly get all you got to do is af plus bd. Also notice if c plus e equals plus or minus 1, then both of the solutions are integers, which is helpful. All right. Another issue was that sometimes you'd like to be able to specify ahead of time what the solutions will be. Give me an equation looking like that, having solutions 5 and 7. Can do. It's a little more complicated, though. Here's how you do it. So the solutions you want, call them R1 and R2. Multiply this expression here, call the result ax squared plus bx plus c. Note that's capital A, capital B, capital C, not to be confused with lowercase a, b, and c. Okay, in the equation you choose a through f arbitrarily and calculate g, h, and j using this formula, and now this equation has those as its solutions. Oh, I suppose I should have pointed out this equation is somewhat different. It's got a quadratic numerator. It's a little more complicated than the one I started with previously, but that's okay. It gives us more flexibility. I called this j instead of I because I didn't want to fool the software I was using. They might think I was referring to the square root of -1. No. Okay. All right. And again, this could be, programmed. Somebody could write code for doing that, and then you can algorithmically generate all the equations you want with specified solutions. Okie dokie. Oh, also I wanted to point out, I said the method is that you can pick A through G arbitrarily. Okay, so I'm going to choose A to be the negative of R1. Remember, R1 is one of the numbers that's going to be a solution. And I can do that because A can be any rational number. Well, that means R1 is going to be extraneous. If I plug in, if A is negative R1, we have this equation. So if X is R1, you have a zero denominator. It indicates it's an extraneous solution. So again, I can create extraneous solutions if I need it to be, and I can make both of them extraneous. Choose A to be R1 and choose B to be the negative of R2. That actually answered a question I had as teaching. I never saw in a textbook any example where there are two solutions of a rational equation and they're both extraneous. So I wasn't sure if it was possible. Yes, it is. It is possible. Well, I wanted to show you just some idea, how did I get all these results? So without going into all the gruesome details, the key idea was this. So let's say I start with this equation here. Well, let's multiply by the LCD, which is x plus a times x plus b. Here's the result. Now that looks pretty complicated. However, it's a number times x squared plus another number times x plus a third number equals 0. It's quadratic. And so here I can look at the discriminant. It would be this one squared minus 4 times that times all of that. And the solutions will be rational if and only if the discriminant is the square of a rational number. So like here's the discriminant of that complicated equation. Anything I do that makes the discriminant to be the square of a rational number, it's going to make the solutions be rational numbers. Well, here's another method that you can use. I call it the method of free parameters. Well, I'm just going to pick a rational number that I'm going to call I. And if the discriminant equals I squared, I've got what I need. So this expression needs to equal I squared. Well, that may not help us, but fortunately I can solve for h and get a linear expression. Actually, what I mean is I don't need to take the square root when I solve for h. H equals this value here. If the parameters a through I are rational numbers, this big ugly expression will be a rational number. I will have what I need. All right. Okay, that'll do it. So here's another method, the method of equal coefficients. So remember that I had a result above for this equation here with the one quadratic numerator. And there I said, hey, pick two numbers. I can give you an equation of this form having those as solutions. So how did I do it? Well, here's the equation cleared of fractions. I create this equation having R1 and R2 as solutions. There's the quadratic equation. Well, if this coefficient equals A, if that coefficient equals B, and that coefficient equals C, this equation will be that equation, and the solutions will be R1 and R2. Well, that means I have this system of equations. Well, the natural solution is to solve it for G, H, and J. And that's the result that I gave you above. It expresses the result in terms of these other parameters, which I either know or calculate. Not a problem. But there are yet other methods for getting equations like these. And this one works great if you have a TI-89 graphing calculator. If you don't, just go to wolframalpha.com and it can do the heavy lifting. It's the method of partial fraction expansions. Now the TI-89 can write the partial fraction expansion of a rational expression. In the F2 menu, you choose option 3 called expand. For instance, if you expand this expression, now the denominator, when you multiply it, has degree 2. The numerator is degree 1. So the partial fraction expansion is valid, and this is the result. This is called the partial fraction expansion of that expression. So I can use this to create rational equations with specified solutions, including one or both that are extraneous. Okay, let's example. Okay, I'm going to start with this equation. Now that's a very easy equation to solve. You multiply both sides by x plus 2 times x plus 6. The equation then says x plus 2 times x minus 5 equals 0. So the solutions will be negative 2 and 5. Except, wait a minute, if x is 2, the denominator is 0. So actually, negative 2 is a extraneous solution. But we don't want to give the equation to the students like that. It's just too easy to solve. So we're going to doctor it. Well, I'm going to expand the numerator. I'm going to do x times the quantity x minus 5 plus 2 times the quantity x minus 5. And then I split this fraction into two fractions, like that. So now I have, the original is equivalent to this equation, one fraction plus another fraction equals 0. I can write the partial fraction expansion of the second fraction because his numerator is degree 1, his denominator is degree 2. And the partial fraction expansion of this guy is that expression right there. So now the equation looks nothing at all like what we began with. Now before I give it to the students, I want to multiply both sides by 2 so that we don't have fractions in the numerator. There you go. I can give this to the students. They'll never know, just by looking at it, that the solutions are negative 2 and 5, and negative 2 is extraneous because that denominator is x plus 2. Right. Now you can actually do this with, you can create two extraneous solutions, but I see the clock is advancing, so I'll just leave you to read my paper, which I guess I should put it on the Chafee website for all of you who are watching online. Maybe you can put it with the show notes for this podcast or something like that. All right. So I'll skip through that. I've found an embarrassment of riches. If I have to create an equation, the most difficult thing is choosing which of the methods to do it. I'd like to get into, scroll through this and get into square root equations, because sometimes we teach those too. Let's talk about how you can create a square root equation with rational solutions. Well, let's start out with this form, the square root of ax plus b equals cx plus d. To solve this, you'll have to square both sides to eliminate this radical. That will give you a quadratic equation, because when this expression is squared, you're going to get c squared times x squared. Now again, there's many ways to create equations like this with purely rational solutions. Here's the first method that I worked on. Let's simplify this by defining a new variable, u equals ax plus b. So then this is just the square root of u. And then x equals u over a minus b over a. Substitute that result into here. We have this equation. But notice, a, b, c, and d, basically at this point they're arbitrary parameters. So I don't need to write it in such a complicated way. Let's just call it cu plus d. It's basically what it is. It's a number times u, a rational number times u plus a rational number. So I just need to pick c and d that will make rational solutions. Let's just notice here that any valid solution must be non-negative. If u is negative, then we've got the square root of u, which is I. And we were trying to stay away from imaginary numbers. Okay, so we want the solutions to be rational. Actually, that means u must be a rational number. Because if u is... Actually, I think I may have misstated that. The square root of u must be a rational number, because the square root of u equals this expression, which is rational. What I should have said is u must be a square. All right, so we'll fix that afterwards. I did say solutions must be squared, but I should have said it there. All right. The way you solve this equation is you square both sides, giving this result here. Subtract u from each side. There it is. It's a quadratic equation in u. And so here are the solutions. The solutions will be rational numbers if and only if this square root is rational. Which I say right here, solutions will be rational if and only if the discriminant is the radicand, 1 minus 4cd, is rational. So I'm going to pick a rational number called r, and I'm going to say my discriminant equals r squared. So now the discriminant will be the square of a rational number. Now I need to find the values of c or d, so I would want to solve this for either c or d. Well, it's a little more elegant to solve for d, because the equation has c times u plus d. I'm going to say pick c arbitrarily and then calculate d from that equation. So here's the general result. This equation will have rational solutions if d has this value. And in fact, the solutions will be these guys right here, and indeed they will be squares. All right. And this equation also has extraneous solutions, because anytime you square each side of the equation, extraneous solutions are a possibility. All right. So this is a fairly easy way to create an equation like this with rational solutions. I have an example here leading to this equation. Square root of u is negative 6u plus 1. I'm skimming through this because time is advancing rapidly. I wanted to point out that, yes, just from this equation here, we can get an unlimited number of related equations, all with rational solutions. That's because I defined u to be ax plus b. Well, if u is rational and a and b are rational, so would be x. In other words, if I replace u with rational times x plus or minus a rational, I get a very different looking equation, but it still has rational solutions. In this case, they're not necessarily squares or positives, but they're rational. Well, I wanted to show you what happens when you use the method of substitution. Basically, I'm going to say I want my solution to be r. So let r be a rational number. And if r squared is a solution for u, well, that means the equation is true when r squared is substituted into it. I do that right here. It says the absolute value of r is cr squared plus d. However, the solution we're choosing is really r squared, not r, so we can assume that r is non-negative. What that means is you can solve this equation for d, and we have this result. I can pick a solution, basically pick a solution. I'm picking r squared as my solution, and there's my equation. Okay. I wanted to show you what happens when there are two square roots. It's more complicated, but I just wanted to summarize what the results are. So again, I'm using u to be ax plus b. So we're going to look in the equation of form square root of u plus a number times the square root of this expression equals f. Well, the point is, if you choose any rational parameters c, d, f, and r, subject to the requirement that c squared times d is not 1, then this equation is guaranteed to have rational solutions. In fact, there they are. Those would be the rational solutions. All right. Now, we don't want to overwhelm the students. So notice that when the equation is squared twice, you get this quadratic equation. The unknown is u. The other letters we're going to choose. The unknown is u, so it's a number times u squared minus a number times u plus a number. We don't want this coefficient to be too big. We do not want this one to be too big either. So don't freak out the students. Choose small values for these two numbers right there. All right. Okay. Now the final type of equation that I'm discussing here is logarithmic equations. I'm looking at this form right here. Log base b of the quantity ax minus c plus log base b of the quantity dx minus e is equal to f. This is very common in algebra textbooks. Since it's the base of a logarithm, b must be positive but not 1. The other parameters could be any real numbers, but we're only going to consider rational parameters. And of course, we want the solutions to be rational numbers. So here's how it goes. Well, you use one of the properties of logarithms to compress this log. The log turns addition into multiplication. So it's log base b of this quadratic expression equals f. And then you write the exponential version of this equation. The base is b when raised to the f power, because the value of the log is the exponent. That will equal the argument of the log. Now this is a quadratic equation, because when I multiply this, I'm going to have a coefficient times x squared plus a coefficient times x plus a number is equal to 0. Also, this equation is now more familiar. It doesn't have that weird log thing in it. It's easier to handle. Okay, well, I mean, the easiest way to get rational solutions is substitution of parameters. Pick values for all of these parameters except one of them. And again, you want to keep f and b small numbers. So I said, okay, I'm picking all the parameters except e. Well, if I specify that -2 is a solution, then this equation becomes true when x is -2. That leads to this equation. The solution is e equals 14. Okay, so that means we have this equation. That's the exponential version. If I multiply and get 0 on one side, I get this result. When I factor, I get that result. It leads to these solutions. But wait a minute. Logarithmic equations can also have extraneous solutions. So despite all of our efforts here, well, in general, one of them or both of them could actually be false solutions. Let's take a look. If x is -2, well, for example, when I substitute -2 here, I've got log base 4 of -2 minus 14. That's log base 2 of -16. The argument of a log function cannot be negative in our elementary algebra class. -2 is not valid. Now, for a lot of equations like this, there will be one extraneous and one genuine solution, but not if there's a coefficient there. If there is no coefficient there, if it was just x plus or minus a number times x plus or minus a number, in fact, it has to have one extraneous and one genuine solution. I was able to prove that in one of my papers. Here, though, we don't have a guarantee. So if you plug in x equals 29 halves, 14 and a half, yes, the arguments are positive. So that is the valid solution. Yes, I mentioned here that for this type of equation, in fact, there's always one extraneous and one genuine solution. Well, what I did next is I generalized what I just said right here. I'm thinking of specifying all parameters except e, and I'm using the letter r for the solution. And I'm saying this equation here, well, this logarithmic equation will have rational solutions if and only if e is chosen to be this value right here. So you could use that as a general method. And then one solution will be r, and that's the other solution. Okay, I've got an example of that. Let's scroll through that. Now, I want to give some practical help to math teachers who need quick answers. Here are 6 easy formulas for creating logarithmic equations with rational solutions. And I'm going to derive a couple of them, and then I'll simply state the other 4. So this is sort of reverse engineering. I'm going to start with this equation. X plus b, that's going to be the base of the logarithm, times x minus 1 equals 0. So the solutions for x would be -b and +1. Well, I'm going to expand this, do the multiplying. I'm going to transfer b to the other side. I'm going to factor out x. And then I'm going to take log base b of each side. That's going to be log base b of x plus log base b of this quantity. Okay, there we go. That's a logarithmic equation, and I know that its 2 solutions are those guys. Now, if x is -b, we got a problem right there. So -b is the extraneous solution, but there's a quick formula for getting a logarithmic equation if you just need a quick if you need it really quickly. Well, a similar sort of analysis gives us this result. This equation, log base b of x, you know, I said I would derive the second one, but it's in the paper. I'm going to save some time here. Plus log base b of ax plus 1 minus a times the b to the c equals c. It has these solutions. So there's a little more variety there. Well, by playing similar games, as it were, we can get some other types of equations. This guy, for instance, which is similar to the first, has these solutions, except now -1 is extraneous. Here it's log base bc. And I guess the last one is this one here. The solutions are b to the c and -1. So there's a very wide variety of methods here. Well, there's what we could call the fill-in-the-blank method, which in some ways is the easiest of all. If you don't have time to look up one of my crazy theorems, you can do this. Okay, let's say we want an equation of this form. Square root of ax plus b equals cx plus d. And let's say we want 5 to be one of the solutions. Well, basically, I just got to fill in a, b, and c, and d so that this works. So hey, just pick values of a and b, so that a times 5 plus b is a square. And then just pick values of c and d, so that c times 5 plus d equals the square root of that square. That's easy. So like over here, I said, hey, square root of 7 times 5 plus 1, well, that's square root of 36. That would be 6. So I just need to have 6 equals a number times 5 plus another number. Well, that's fairly easy to do. 2 times 5 plus -4. So the 5, well, the 5 is x. The 5 is x, so there's your equation. And then I show the details, squaring both sides, getting 0 on one side, factoring, we have these solutions. I also noticed that if we were to say that this square root is -6, and it doesn't because the square root symbol, by definition, is positive or non-negative. But if we pretend it is, then we would have this equation here. Oh, this time I choose different values for c and d. That gives us this different looking equation. But we still get valid solutions. This time, 5, the number we chose, is extraneous. And the other one turns out to be a rational solution. So for the purposes of creating an equation, it's okay to pretend this guy equals -6. It all works out. Now you can also use the fill-in-the-blank method for logarithmic equations. That's not quite so quick because you have to make a transition from, you want a logarithmic equation to this form, you got to change to the exponential version of the equation. You should begin by choosing b and f. So I chose 4 to the 2, which is 16. So now I need to fill in the blanks on this equation here. I wanted -3 to be one solution. So now I need to find a, c, d, and e so that this is true. Well, I need to make this one and that one to be factors of 16. So I could make this 16, I could make that one 1. Or I could make this one to be 4 and that one to be 4, or etc. So I guess it's fairly obvious how to do it, and I have an example in my paper here. And you can also do this for square root equations with 2 radicals, and again, the reason is you just pick blanks. Okay, so here I'm saying that I want 3 to be one of my solutions. I fill in these blanks to make the first radical to equal a whole number, and I fill in these blanks so that this radicand is a square, and then I just pick this number to be whatever I get from filling in these blanks. Okay. I'm thinking probably the basic idea is pretty clear here, so I don't think I need to run through that example. But I've still got some more tricks up my sleeve. I'm only on page 26 of 31. Actually, in some ways, the best is yet to come. Oh, I wanted to point out that with the square root equation here, it's not that difficult to get a fractional solution, to get one of your solutions to be a fraction. You know, I just put numbers here to cancel the fraction, and then I just pick C and F, so it'll work. The only difficulty is making sure that the equation you create is not going to be too difficult. The reason is to solve one of these equations, you've got to square twice. And every time you square, a small number can get big. And if you square twice, a small number can become colossal, making it too difficult for the students. In fact, I thought an example... no, I don't have an example of too colossal here. This one worked out nicely, but you got to vet your equations to make sure they don't become overwhelming. Just because they're rational solutions doesn't mean it's going to be easy for the students to solve. Okay. Well, I've discovered yet another method, which in some ways is the best of all, or at least my favorite. So I just called it the x minus r method. Okay, let's start by noticing that if p and q are non-negative, then this equation is clearly true when x equals r. If x equals r, this is 0, and you've got the square root of p squared, which is p. If x equals r, this is 0, so you got the square root of q squared, which is q. So the left side is p plus cq, and that sure does equal p plus cq. So this guy is true when x equals r. R is a solution regardless of what p, q, a, r, c, and d are. So one solution of this is r, and there's the other solution. Now, this gruesome expression does tell us one important fact. The denominator shows us that if a minus c squared d equals 0, there is no other solution, meaning that there's only one solution. Meaning that when you square twice, you get a linear equation, not a quadratic equation. That's very helpful. Sometimes we want to have a little mercy on our students and not force them to solve a quadratic equation. All right. So there's an example of doing that. Let me see, is there any details in there worth emphasizing? Well, so if x equals 1, then we will have a solution because of the way that I set it up. If x is 1, the left side is 2 plus negative 1 times 4. Yeah, okay. So there's your equation. Now you got to isolate one of the roots. You got to square both sides. You still have a root, so you got to isolate the other root. Oh, this one's going to give us a big number. Yeah, when you square this side. No, actually, that 289 is canceled out by this 16 times 4. Okay, it's not too bad. All right. And so we get two solutions, one of them being extraneous. And you can also do this if there's only one square root. Again, if x equals r, the left side is p, and the right side is also equal to p. And we have a valid solution. Okay. Well, you can use the x minus r method to create a rational equation with a specified solution. I'm going to aim for a equation having this form again. So the LCD is x plus a times x plus b. I need these two factors to be the same as those denominators, or else it's just too difficult for our algebra classes. Well, here's how you do it. I'm just going to start by adding two fractions. And I chose denominators that are relatively prime, but I'm not sure you have to. I just felt it would look better if you do. Okay, so this is a true equation. Now, to make an equation with x in it and with r being a solution, I just do this. I take my 3 and I add a times x minus r. And over here on the denominator, I add b times x minus r. So everywhere I add a number times x minus r. So if x equals r, that's 0, that's 0, that's 0, that is 0, that's 0, that and that are 0. And I'm left, the equation becomes this one, which is true. So I have an example of that. I want -3 to be the solution, so I just have a bunch of x plus 3's there. And I just choose values of a and b and c and d, and there we go. Actually, oh, I chose b and d first just to make each step a smaller step. After choosing values of all the parameters, I finally get this equation, and there's no way to see where it came from in that equation. And indeed, according to my TI 89, the solutions of this are -3, the one I specified, and there's also -11, and they will both be valid because neither one of these makes the denominator 0. Okay. So I would say of the methods I've shown, if you have the technology for quickly simplifying or solving equations, probably the method of substitution is the easiest. It's probably the easiest way to do it. It's not necessarily the most fun, but it's the easiest. And I also wanted to apply the x minus r method to this logarithmic equation right here. Here's how it goes. So I'm going to pick a value of b for the base and f being the right side of the equation. I'm going to calculate b to the f, and I'm going to find two positive factors of b to the f. And it could be the trivial factorization, where p is 1 and q is b to the f. Well, then I just do this. Log base b of the quantity p plus a times x minus r plus log base b of the quantity q plus d times x minus r. When x equals r, these terms go away, those terms go away, and we will in fact have a solution. Now if you compress the logs into one log, as we did before, and write the equivalent exponential equation, we have this equation here. So if this term is 0 and that is 0, the equation says p times q equals b to the f, which is true because of the way we chose p and q. So I recently created an equation for an exam using this method, and it was very easy. Also, it's easy to control. The main thing you've got to control is the size of b to the f. If b and f are too large, that can easily get out of hand. So here's an example. Let b to the f be 3 to the 2, which is 9. And let p be 9 and q equals 1. And now let's say I want -4 to be a solution. Plug in the values. I'm going to have this as my quadratic version. Assign values to a and d. Now I still have to vet this equation to make sure the coefficients are not too big. I would have this expression here. Well, when I multiply these and subtract 9, I have this equation here. I don't like 252. Now, if my students have been paying attention, they would be able to factor it, but it might take a whole long time. So I said, the problem is 29. That's too big. So I got to go back and fiddle with the numbers. So this time I came up with that equation. That's not too horrible. And in fact, in this case, so that we get these two solutions, now there was the original equation. Actually, neither solution is extraneous. And partly it's because of the 5 minus x. Usually in our business, in teaching, we say x minus 5. 5 minus x is a little unusual, but it works. And I think this is my last point of my paper. This is not something we can give in elementary or intermediate algebra, maybe in college algebra if you have an exceptional class. Well, if you don't mind the cubic equation, we could start with p1 times p2 times p3 equals b to the f. And we can do one of these right here. We now have 3 factors. If x equals r, the left side reduces to p1 times p2 times p3, which does equal b to the f. Well, that would give rise to this logarithmic equation. However, I don't know, it might be against the ed code to give our students an equation like that, so I'll just keep that in mind as a possibility for the future. Well, that concludes my presentation. I hope you found some inspiration for ways to make composing equations a little bit easier. Like I said, I understand this video is going to go on the Chafee website. Maybe we can have a link to a PDF of the paper so you can look up all the gruesome details for yourself.